Hello, everyone. Good afternoon. How are you? Okay, so today we do section 4.5. The definition of a new stochastic integral. So we are going to define the new stochastic integral from A to B of phi t dbt, where phi t may not be adopted with respect to the filtration given by the Brownian motion Bt. Oh, by the way, in this section, we make the assumption so that I don't need to mention this every time. All stochastic processes are assumed to be continuous. Okay, so this is our new stochastic integral, and we are going to define it today, or in this section. Of course, we have done a lot of example already, and the key idea is we decompose the integrand phi t into decompose phi t in terms of two things. First, the adaptive stochastic processes, and secondly is the instantly independent stochastic processes. Okay, so now we are going to define it. Step 1. Step 1 is for the case the integrand phi t is the product of ft and phi t with f being adopted and g being instantly independent. This is the first case. Now, through the motivation in the previous section, previous several sections, we define this. So this is the definition. The integral from A to B of ft phi t dbt This is defined to be the limit as the mass of the partition goes to 0 of the Riemann-like sum I from 1 to n. F, the evaluation point at the left end point, and the evaluation of phi t is at the right end point t sub I. And then the Brownian motion increment on the interval from t sub I minus 1 to t sub I. This is defined to be this limit, provided that the limit in probability exists. And here, the situation is this. Oh, maybe I use oh, that's okay. This is A, this is B, and the subinterval from t sub I minus 1 to t sub I. The Brownian motion increment here is over this subinterval. And now the evaluation of F is at the left end point. The evaluation of the instantly independent stochastic process phi is at the right end point. So this is for adapted vector. And this part here is for instantly independent stochastic process phi t. And if the limit in probability of this Riemann sum exists, then we define the limit to be the value of the new stochastic integral. And that is for step 1. Okay, let's change to a new page. This is page 23. Now, immediately we have this question. Is this stochastic integral well defined? Namely, which is the integrand can be represented by ft phi t, and it can also be represented by gt psi t. For examples, bt times b1 minus bt. This is the product of adapted and instantly independent. So we can think of bt as ft, b1 minus bt as phi t. But this is equals to what? For examples, let's put 1 plus t squared ft times 1 plus t squared, and this is, oh, I'm sorry. bt. And this b1 minus bt. You see this 1 plus t squared, 1 plus t squared cancel out. But this is, you can think of this as a gt, and this as psi t, and they are equal. And so the an integrand can be represented by several ways. This is one way, this is another way. And then the question is this, whether the limit as the mass goes to 0 of the summation I from 1 to n of f ti minus 1 and phi ti equals to the limit summation. Here, this is the Brownlee motion increment. G T I minus 1 psi T sub I. Whether they are equal, the limit. If the limits are different, then the stochastic integral in the above definition is not well defined. Note that this equality does not imply this equal to that. As point made as obvious because here this is the same t, but here is different t's. Okay, so that is the question. And now we're let's put this as equation 1. So we need to prove equation 1 in order to show that the stochastic integral is well defined. Okay. Now, by lemma 1 in section 4.4, there exists a continuous function alpha t such that g t equals to alpha t times ft, and phi t equals to alpha t times psi t. This is from lemma 1. And now we turn to the next page. This is page 24. Therefore, we have summation I from 1 to n of ft sub I minus 1 phi t sub I, the Brownian motion increment. That equals to summation I from 1 to n f t sub I minus 1. And now we replace phi t. Phi t equal to that. Yes. So phi t is alpha t sub I psi t sub I. And then that equals to summation I from 1 to n. And now I'm going to push alpha to the front of f. So alpha t sub I, f t sub I together. And now you see here, this is t sub I, this is t sub I minus 1. When this alpha is regarded as the multiple of f, you see the evaluation at a different point, but we need to have the same point. Now note that alpha is continuous. If alpha is continuous, we can replace alpha t sub I by alpha t sub I minus 1. And now you see the same t sub I minus 1. And of course, this is not equal to that, but almost equal to the sum I from 1 to n. And by taking the limit, it's the same. Okay, and so you see, we have shown this. Okay, now, so that equals to what? Now, summation I from 1 to n. Now, alpha times f is alpha times f is g. So the first factor is g of t I minus 1, and then psi t sub I. Okay, so we have shown that this Riemann sum, this Riemann sum, they are almost equal in the sense that the limit are the same. This implies that the integral from a to b of ft phi t dvt is the same as this. And so the new stochastic integral is well defined. Okay, so this video we stop right here.